We all receive a minuscule daily dose of radiation from cosmic rays and radioactive substances in the soil. We may also come into additional radiation exposure from things like television sets, dental X-rays, and other man-made sources. Although this background radiation is really unavoidable and very minute, higher levels can be harmful and even life-threatening because radiation is composed of high-energy particles and waves that damage cells and disrupt key biological processes, often causing cell death. A difficulty with observing radiation and detecting it is because it can't be directly measured or directly detected by our senses. So we can't see it, smell it, taste it, hear it, or feel it. So there are instruments that help us detect radiation, such as a Geiger counter, which is a small portable device that contains a gas which is ionized when it comes in contact with radioactive substances. And perhaps you work in a medical field or an area where you might be exposed to radiation, and in that case you may wear a radiation badge and protective clothing. The radiation badge contains photographic film that fogs when it comes in contact with radioactivity. These badges are regularly monitored to ensure that the individuals are not exposed to unhealthy levels of harmful radiation. A common unit for radiation is named after Madame Curie, called the Curie, and the international system is called the becquerel. Now, while in this course we're not going to emphasize or we're not going to go into great detail about measuring human exposure to radioactivity, we still can use what we've learned in terms of conversions to answer the following question. A patient must be given a 4.5 millicurie dose of iodine-131, which is available in a solution that contains 3.5 millicuries per milliliter. Anytime you have a relationship like this where one unit is over the other, so 3.5 millicuries over 1 milliliter, this can be used as a conversion factor. Looks familiar. And so we don't start the problem with the conversion factor, but we think that the person wants the 4.5 millicurie dose, and we know that we have a 3.5 millicurie per milliliter solution. So putting the 3.5 millicurie on the bottom, so the units cancel, and the 1 milliliter on the top, we can answer this question and calculate the volume of this solution that would need to be administered. And so dividing this, we get 1.3 milliliters of the solution would need to be administered to give a 4.5 millicurie dose. Now, I mentioned this previously, but one of the reasons we have concern over radiation exposure is because radiation is what is called ionizing radiation. And so ionizing radiation ionizes or excites molecules that can cause changes that affect the function and the metabolism of the cells. Cells that are most sensitive to radiation are those that undergo rapid cell division. In a healthy body, it's things like bone marrow and reproductive organs, skin, and your intestinal tract. This is also true for children who, as a general rule, have cells that are growing faster than adults. We use this sensitivity, though, to our advantage because cancer cells often undergo rapid cell division, and so they're sensitive to radiation. So we can use a radioisotope to help kill and treat cancer cells. So a way to protect yourself from radioactive substances, if you were to work with them, has to do with what you're actually working with. So alpha particles which are the largest and have the least penetration, you could use lab coats and gloves. Beta particles, which are smaller and can penetrate further, you would still only be required to wear a heavy lab coat and gloves. But gamma rays, which have the most energy and travel the fastest, can readily penetrate the body tissue, and so this you would have to work behind a thick lead shield, along with the gloves and lab coats. One thing I think I didn't mention here is it's always best to wear goggles when you're working in the lab. Now, medical uses for radioisotopes are quite plentiful, and we have two big categories. In this course, I'm not asking you to memorize or learn the different uses for different radioisotopes, but know that with modern technology, radioactive isotopes are very useful in medicine. Not only do they help us diagnose different illnesses and diseases, but they also help in the treatment of those diseases. So chances are, if you work in the medical field, you will encounter some radioactive isotopes.